Hi everyone, I'm presenter Seungyeon Kim from KAIST AI. In this video, I'm going to present our EMNLP paper. The title is DocKD Knowledge Distillation from LLMs for Open World Document Understanding Models. So let's get started. Here's the quick preview of our work. In this study, we aim to improve the generalizability of visual document understanding (VDU) models, such as DocFormer or Layout LM. For this, we distill knowledge from LLMs, which, given instructions to elicit open-ended answers, can create rich and diverse annotations. LLM generates document annotations for VDU tasks using unlabeled document library that is publicly available. And we present DocKD, a document knowledge distillation framework that leverages external document information to enhance LLM data generation. This is a core contribution of our work, and this external knowledge helps LLM understand non-textual information and produce better, higher quality data. And here's the introduction. Visual document understanding, shortly VDU, requires extracting and analyzing both textual and non-textual information from a document. The non-textual information is visually rich, demanding a solution to directly process the document image. Recent approaches have proposed multimodal document understanding models to address the model's comprehension of textual, visual, and layout features. However, the existing VDU methods are limited by their generalizability to diverse documents. They are typically trained on a small-scale, curated document dataset. So their performance heavily relies on the annotated training document set for downstream tasks. To address this limitation, in this study, we aim to improve the generalizability of VDU models. For this, we leverage LLMs to generate document annotations given the text extracted from a document image. For instance, we might instruct the LLM with a prompt, generate question-answer pairs from this document, along with document text extracted from OCR. However, this approach entails a critical challenge because LLMs often struggle to comprehend unstructured OCR text, leading to its generation of low-quality annotations. Moreover, there is a variety of non-textual information within documents, which is not included in the LLM prompt. To overcome these challenges, we present DocKD, a document knowledge distillation framework that leverages external document information to enhance LLM data generation. In this framework, we extract various document elements such as key value pairs, layout, and descriptions, along with text, and formulate a generation prompt for LLMs with this visual information. The LLM outputs then serve as annotations to train a small-scale VDU model. Our approach is similar to visual instruction tuning, where LLMs are employed to generate the visual language instruction following data. Our work is the first to extract knowledge from LLMs for open document understanding tasks, and we explore methods to inject visual document specific knowledge into LLM and produce high quality data. So this figure is the overall pipeline of DocKD. In A, we first construct a generation prompt, pgen, for the task. Then, given the generation prompt and document text as inputs, the LLM generates the generative answer. This generative answer is parsed into the task prompt and task answer pair, P task, A task, by post-processing. Here we can inject document-specific knowledge into the LLM inputs so that it can better understand the document contents and generate more accurate P-task, A-task pairs. In B, we train a student video model to output a task answer given a document image and the task prompt. So we exemplify the application of our training pipeline on 3 document understanding tasks, which are visual question answering, entity extraction, and document classification. So the document VQA is the task of answering questions about documents. Our task prompt and answer are designed as follows. We have document, the text, and question Q, and the answer is A. LLM generates data, and this A-gen will be parsed into questions and answers that construct the task prompt and answer. However, OCR text is a simple sequence of words typically ordered by raster scanning, which ignores the important layout and structure information of document pages. Therefore, QAs generated from such text are usually less challenging and do not cover the spatial relationship between entities. To ensure the LLM's awareness on the text layout, we replaced the raw OCR text with spatially linearized OCR text, where we organized the document text into a markdown style. Thus, the linearization model supplements document layout knowledge that is missing and helps the LLM to generate more diverse and higher quality QAs. Entity extraction aims to identify entities in the document that matches a given field name. So the task prompt and answer are designed as follows. Given the field name F and the corresponding entity E, we have question, what are entities of F, and the answer E. And LLM generates the field name and entity pairs. So LLMs are able to capture a group of words into a single entity and generate a field based on the context. Although LLMs can identify entities from documents, they are unable to sufficiently enumerate all the entities. They tend to list mostly the major ones, especially when there are many potential entities in the document, and fail to identify diverse types or names. To help LLMs to enumerate all of them, we detect all key value KV pairs using an external KV detection model and send the detected KV pairs to LLMs to obtain their field names. And we do this in an iterative manner. So we first have the first entity E1 and LLM produces the field name for this F1, and then we insert the F1 and E1 pair, append this into the generation prompt, and along with E2 produce F2. That's the second field name, and so on. So this makes the LLM focus on the field generation only for the current KV entity. In addition, it has access to previous generated outputs, so if there are similar entities given, you can assign the same field name. Lastly, document classification. So task prompt and answer here are what is the class of this document? Choose from the following candidate list, and the answer will be class label. And LLM has to generate not only the class label but also the candidate list. So we need 2 types of generation prompts. For positive labels, which would be the answer class, and the negative labels, which is not an answer but is included in the candidate list. So LLM frequently generates class labels that are overly general with low diversity. So we incorporate document descriptions to the generation prompt, facilitating LLMs to better summarize a document and generate more diverse class labels out of it. The first step of data generation is generating document description, like describe this document in one sentence. The output document description is then appended to the generation prompt for positive labels. This strategy makes the positive labels more diverse and detailed based on the description. Subsequently, we also use the output positives in the negative generation prompt in order to avoid generating labels that are similar to the positives. We train the model to choose one among the positives and negative list. And also the generated description is appended to each positive label to give a hint about the class. In our experiments, we evaluated DocKD on the open world video tasks. DocKD utilizes Cloud 2 Teacher and FLAN-T5 and DocFarmer V2 as a student video model. And compared to the plain KD with raw CR text, DocKD significantly enhances the performance. So this figure visualizes some sample data generated by using KD and DocKD respectively. For document VQA in A, DocKD generates more challenging QA pairs that requires understanding the structure of the table. And in B, entity extraction, DocKD is able to capture significantly more entities than KD. And for document classification in C, DocKD generates a document description, which helps to give class labels that align better with the document contents. So please refer to our paper for additional experimental results, including the comparison between various teacher and student models, statistics of generated data, and combining DocKD with human-labeled annotations, which achieves significant performance in video tasks, and also for the generation prompts and the generated data examples. So if you're interested, please check out our full paper and feel free to visit the virtual poster session and email me if you have any questions. Thank you for tuning in.